Hi, everybody. Thanks for sticking with me in this last talk of the conference. So I'll try to present some things about JuliaSmoothOptimizers, and to avoid saying this a lot, I will just say JSO. Okay. Yep. So to give you a very short context, well, you are all optimizers, so you know all this. I will mainly focus on continuous nonlinear optimization. Okay. So I'll just keep this in mind throughout my talk, that I'm considering an optimization problem. I have a function, I have constraints, and I want to use derivatives of all this. Okay, so if I'm trying to solve the problem, I'm trying to find a stationary point or local minimum. Okay, so that's basically the context. So I wanted to give a very brief genesis of JSO. So JSO is a GitHub organization that contains collection of Julia packages. It's mainly focused on numerical linear algebra and continuous optimization. The organization was initiated in 2015 by Dominique Orban and Abel Siqueira, and now we have more contributors. Mainly core contributors are researchers in numerical linear algebra or optimization. And JSO is used mainly, well, it's used in the classroom, it's used to write research paper and to solve large problems. And I'll take the opportunity to thank all the contributors to JSO packages. And as you see, there are some room left at the bottom, so I hope to see more of you there next year. And so the JS organization is quite large and getting more and more popular. What I want you to keep in mind on this slide is that we have now 60 registered packages, which is a lot. And we are trying to investigate ways to maintain all these 60 packages. And so I'll just give a link to Abel Siqueira's talk at the JuliaCon from last week, where he presented something called the Bestie template, which is trying to promote best practices and try to automatize all this in the packages so that it helps us maintaining these 60 packages while we are only 3 or 4 working on all this. Yeah. So please have a look at this. And to give you a very short idea of what these 60 packages are, it can be split in 4 parts. We have modeling packages, solvers, linear algebra solvers, and various tools like test problems or internal tools for unit testing, CIs, and stuff. Okay. And I also wanted to give you like a very brief example of the type of research we are interested in with JSO. And one example is an algorithm called ARC that stands for Adaptive Regularization with Cubics. So it's an iterative algorithm to solve unconstrained smooth optimization problems. And so basically at every step, you want to compute a search direction, and this search direction is the solution of a cubic unconstrained problem, okay? So that's why we have the cubic name. And the very important fun fact here is that the complexity upper bound of this method to find, so the number of iterations to find first order stationary point is an epsilon minus 3.5 for ARC method, while it's only epsilon of minus 2 for steepest descent or stressed region method. So interesting theoretical facts, and so then you want to work on implementations. And the main ingredient in these methods, it's sort of the same as in stressed region method. And it's the same sort of all the time when you want to implement optimization solver. It's some linear algebra stuff in the end. So the key ingredient in this algorithm is to solve these shifted linear systems while at the same time searching for the appropriate shift. Okay? So if you don't pay a lot of attention to the implementation, you will try to solve this for one value of lambda, check if lambda is working for you, and if not, you'll have to resolve it again. Okay? And so one idea that we developed in this paper is to exploit some Langshaw's implementation of the conjugate gradient to actually solve this linear system for several shifts simultaneously. So you don't have to resolve it. You will actually solve the linear system for a bunch of shifts that are predetermined, and then choose the appropriate one. And so this is possible thanks to a refined implementation of the conjugate gradient that allows to do just one matrix vector product, and this for many shifts at the same time. Okay. So this is one example of a study we did in JSO, and then so you have to do a lot of theory, and then implementation is getting very easy thanks to JSO packages. You just use krill.jl, which contains a lot of numerical in algebra iterative solvers, thanks to, shout out to Alexi for that. You combine this with NLP model, solver core, and then you get your package with your implementation of the method, okay? And if you go one step ahead, you use qtest.jl and solver benchmark, and you have your paper with numerical results, okay? Perfect, so maybe I can give you some small insights on how it works internally. So one of the core packages in JSO is nlpmodel.jl, which provide an API for model of this form, okay? So nonlinear continuous optimization model, okay? So essentially it defines abstract rules that solvers can rely on independently of the modelization, okay? So you think, oh, I have this optimization problem, I will model it with jump, and then some package will take care of translating this in NLP model, and then you can use any solver in JSO, okay? And perfect, and so essentially the NLP model API defines a set of rules to access the function, the objective function, the constraint function on their derivatives, okay? And then it will make sure that you can access the derivatives to access either the Jacobian or Hessian matrix, or just maybe to compute Hessian vector product or Jacobian vector products, okay? And for this, just matrix product operations, we rely on linearoperators.jl, and for full matrix evaluations, we use zero structures. Perfect, so that's for the modeling part, what the solver is assuming from the problem. And then what we call the JSO compliant solvers is just two rules. We assume that the input must be an instance of an abstract NLP model, and the output is a generic execution stat that will just contain basic things that you would expect the solver to return, okay? And that's it. And yeah, and based off these rules and based on the NLP model API, we implemented a bunch of solvers, and you can also have access to wrappers to existing solvers. So we have wrappers to Artemis, Nitro, IPOpt, AlgenCan, and pure Julia implementations for a bunch of different problems, unconstrained, bound constraint, RibQP for quadratic programs, Percival, and so on and so forth, okay? And what's great is that when we develop all these solvers, they are independent of the origin of the problem. They just assume that you give us something that respects the NLP model API, and then you choose how you implement, how you use the structure of your problem. Perfect. Yeah, so maybe one pointer to JSO Suite. So you've seen in this slide that there is a growing number of solvers, and sometimes it's very hard to find which one I should use. So that's why we implemented a package called JSO Suite that will be like it's aimed to be a simple, intuitive entry point to this JSO universe, okay? So this package will help you find the right solvers, hopefully, and maybe we are trying to add automatic detection of some structure of your problem to help detecting, let's say, either it has linear constraints, is it a non-linearly square problem, and so on and so forth, okay? So essentially, with JSO Suite, you don't have to know all the packages that live in the JSO universe. You can just use this to solve your problem, okay? And connected with solver benchmark, you can run benchmarks, collect results, print performance profile, and so on and so forth. Great. So that's for the solver part. The modeling part, so the NLP model API, as I said, is defining an abstract set of rules, but we also want to implement things. So you could, we have one package called AdNLPModel.jl that use automatic differentiation to compute the derivatives of your problem. You can also use manual NLP model to feed yourself the function and the derivatives, and some other packages that exploit the structure of the problem. And one example that I like is PDNLP model. It's one package that is designed for PD constraint optimization problems and use grid-app.jl to discretize the PD with finite elements methods. And then PDNLP model takes care of respecting the NLP model API for this. And one other example, of course, is you can use jump models, and we have one package called NLP model jump to help translating a jump model to NLP model or connect also with MY. So with MY, I think you should be able to use any JSO solvers as well, thanks to Benoit's work. And what's great is that independently of the way you decide to implement your model and respect the NLP model API, it doesn't change anything for the solvers. Okay. Great. So I won't talk a lot about AdNLP model. I just wanted to mention that there has been some new updates there, thanks to Alexis, Guillaume Dahl, and André Hill, that led to massive improvement in the Jacobian and Hessian computations. So I invite you to ask us a question or discuss this after the conference if you want, or ask Alexis. So essentially in the AdNLP model, we are trying to be up to date with what people are developing in automatic differentiation in Julia, and trying to be as flexible as possible so that you could use different backends, different AD systems. And also you can, I'll skip that. Yeah. Great. So things I won't talk about in models is that you can also, of course, specialize further this abstract API. So one thing we like a lot is nonlinear least squares problems, where your objective function is not just a nonlinear function, but you know it's a sum of square. Okay, and for this type of problem, you probably exploit the fact that you know the residual function capital F, and maybe design method that only relies on the Jacobian of this function. So it's very useful to have access to this function directly and not through the objective function. Okay. So you can specialize this. You can also add modifiers to your NLP model, meaning you give me an NLP, I apply something on this that still gives me an NLP, and I can just apply my solver the same. So one very basic example, it's something very new that's called timer NLP models. So let's say you give me an NLP here. So NLP model test is containing a set of test problems. Okay, so I have an NLP, and I'm using timer NLP on this, which is a modifier of the model, and it's still an NLP model. So I can apply my solver trunk on this, and then maybe have some extra information. So timer NLP model is just a very thin layer to have some benchmark information on the problem's evaluation functions. Okay, so here you'd have some statistics on how many times the objective function or the gradient have been called, the number of allocation, the time it took, and so on and so forth. Great. I also wanted to share, so if I have a bit of time, some work in progress. Essentially two. The first one is JSO GPU support. So we are trying to propagate unit tests and benchmarks on GPU across all the organization whenever it's possible. And so this is pretty much work in progress. Most of the model have this unit test on GPU now. Some solvers, hopefully equality constraint solvers very soon. and later quasi-Newton methods and solvers with inequalities. Okay, and so this works because, for instance, in Fletcher and Percival, those are factorization-free methods. So we rely on Krylov on GPU as a key building block there. And one last work in progress, it's called parameter optimization. So as I said, a minimal JSO compliance solvers is you take an NLP model as input and you return a generic execution stat. Actually, there is another secret rule that I'm calling efficient JSO compliance solvers, is you implement actually this function solve for in-place solving of your problem. Okay, so most of the solvers that I described before are actually allocation free if you use this. So meaning if you pre-allocate the solver structure here and the stats, shouldn't be using any extra allocation. Okay, and we are adding something new that's called an abstract parameter set to specifically handle the parameter of your problem. And then the workflow goes like this. You use abstract parameter set, you specify bounds for your parameters, default value, and then we instantiate another optimization problem whose role is to find the best parameter for your solver. Okay. And then you solve this problem with derivative-free solvers or random search, or I don't know, and feed the solvers with your new optimized parameters. And what we are working on is to make this whole process automatic so that it opens a pull request on your repo and says, oh, I think this is better default parameters. And so this is all a work in progress, but I'm quite happy to share it with you. Well, this is an example of the code, but I think you got it. And thank you all for your attention. And I'm happy to listen to questions.